Professor Muhammad Sabieh Anwar. I actually also like his name because he's also MS Anwar as me. So Professor Sabieh Anwar, he's working in Lahore University of Management Sciences, LUMS. He is also on Ahmad Dawood Chair and Dean of LUMS Syed Babar Ali School of Science and Engineering. And he played the most crucial role in establishing the physics department at LUMS and among the principal founders of the school's experimental facilities and curriculum. And he actually also doing a very important work in improving the science in Pakistan. So for that, they are actually arranging the science mela every year, which is in fact establishing the ground because they are targeting the schools students and improving their science. So here we welcome Professor M. Sabieh Anwar for his talk. So
thank you very much, Dr. Shabazz, for giving me the opportunity to share some of my work here. So let me share my screen.
yes.
Yes. So, Dr. Shabazz, can everyone see my screen right now?
Yes, we can hear you very well and also see your slide.
Right. So today I would like to talk a little bit about some of the recent work that we've done with quantum mechanics in our laboratory. Generally, when we teach quantum mechanics to our students, it's very dry, it's lifeless, and that's why in Pakistan, quantum mechanics really doesn't.
So I guess there is a connection problem. I guess Dr. Sabieh has some connection problem. Oh yes. Your microphone is off.
I'm so sorry about that. There's no problem here. So I would like to share my work on implementing quantum mechanics in the laboratory. And
Could your slide?
sorry, can you? Okay.
Yes.
So, so I would like to discuss some of the recent work that we've done in regards to setting up a quantum mechanics laboratory in our university, which is primarily meant for the teaching of quantum mechanics, but is also a sandbox for research in quantum optics and quantum information processing, the fancy word of which is quantum computing. Just some advertisement here. Just a couple of days ago, we also produced a textbook which describes this work. This textbook has been published by the Institute of Physics in the United Kingdom. So you're welcome to have a look at the contents of this book. And this book provides the underlying theory for quantum information processing. If you would like to learn about quantum computing, how are they built, what is decoherence, what is entanglement, and how do you actually build experiments using meager resources to demonstrate quantum information processing, then this is probably a book that you would like to keep in your library. So the basic idea behind our laboratory is the following. We have a laser beam that strikes a crystal, in fact a pair of crystals, beta barium borate crystals, and two beams come out, and these beams comprise photons. I'm going to keep the discussion very simple here because there's an audience with a very wide background here. So when these light beams come out, each light beam comprises photons. Suppose I input 100 photons into this crystal. Now, this process, which is called down conversion, is an extremely inefficient process. So out of 100, if the efficiency of this process is 10 raised power minus 10 perhaps, then out of those 100, very few photons will emerge. Hardly any photon will emerge from this beam. But if I use a high power laser, still I can expect to get a reasonable photon flux in one of these beams. But still the flux would be so small that I can actually consider that a single photon is coming out of this path and a single photon is coming out of this path. So just to give you an example, one photon is seen in the upper path, and in order for the next photon to come in, you would have to wait a few, say, microseconds. And microseconds is a long time scale when you consider the speed at which these photons are moving, which is the speed of light. So what I've in practice done is I've created a stream of single photons, one photon at a time, just one coming into the apparatus. Imagine a laser which has zillions and zillions of photons coming out. And if I attenuate the laser beam such that there's just one photon in the apparatus, then I have a single photon scenario. So this is how we generate single photons in the laboratory. These photons fall onto special detectors, which are called avalanche photodetectors. And these detectors have the property that they respond to a single photon. So a single photon hits a detector and it produces an electronic pulse. Now, these electronic pulses from the various detectors then go into counting units. So you can count the number of pulses that are coming in channel A, channel B, channel B prime. And then you can do different kinds of statistics with these photon counts, as they are called. You can also do what is called coincidence counting, which means there is a photon both in channel A and channel B at the same time. Now, this is where quantum mechanics plays an important role. If a single photon comes in, we know that a photon can't be split. So if this detector A registers a photon, B must be silent. If B registers a photon, A must be silent. So which actually shows that a single photon exists and it can't be split up. It's a fundamental particle. So with the help of these single photon sources which are produced by this crystal and single photon detectors and carefully designed electronics, we can do a lot of gimmickry. We can do a lot of acrobatics with quantum states, and we can count photons, we can look at entangled photons, we can see whether a photon interferes with itself, etc., etc. So this is the basic overview of our laboratory, and this is what the laboratory looks like. This is, as you know, this is an optical table. All the optics is laid out here. Here on the top right, you can see the crystal, the down conversion crystal is held in a typical mount. A breeze of dry nitrogen bathes this crystal because it's hygroscopic. Here at the bottom left, you can see the 4 single photon detectors. Light is in the free space, and then it hits a certain adapters and it goes into the optical fiber, and from the optical fiber it goes into the single photon detectors, and then you do the electronics and count the pulses. So in order to do the counting, we have written a program on an FPGA, which is a field programmable gate array, which is a versatile piece of hardware. You have to program it, and then all the data goes into the computer, and then we write a LabVIEW program that can look at counts on different kinds of detectors, and then you do the statistics. You invoke your knowledge of quantum mechanics to look at interesting things. And what are those interesting things? Let me explain in a minute. So this is the basic scheme of an experiment. You have a laser. This laser is aligned, and the laser is polarized. With the help of this half-wave polarizer, you rotate the polarization of light. This light then falls onto a crystal. Most of the light passes unscathed, goes straight through, and is blocked. However, there are two beams that come out, as I mentioned earlier, at a certain small angle. And since it's a highly inefficient process, the flux of these photons on the side arms is extremely minute. And the flux makes these beams qualify as single photon light beams. Then you can do some focusing. You can change the polarization state again in one of the beams. You can have a polarization beam splitter, which transmits horizontally polarized photons in one direction, vertically polarized photons in another direction, and then you have these detectors which can count single photons, and then you look at the statistics. And this is what the actual photograph of a setup looks like. You can see the light beam, you can see the beam block, the crystal, different kinds of polarization manipulation stages which are controlled with motors, and all of this then falls onto the detectors. And in fact, the detectors are placed in this light shield box. Since these are single photon detectors, you have to protect them from ambient light. They will burn out if they are exposed to ambient light. They are meant for looking at single photons. Now, I've already explained the process of creating single photons. Light falls onto a pair of crystals, and the down converted beams come out in two different angles, and then they are detected. Now, the point is that these two photons are produced at the same time. So if I detect a photon at A, I must have a photon at B. So they are correlated in time. And their polarization states are also correlated. Depending upon the input polarization, if this is a horizontally polarized photon, this would be a vertically polarized photon, for example. So in effect, these photons are entangled in time and in polarization. So it's one of those counterintuitive states which are called entangled states that we are producing in the laboratory. Here in this picture, you can actually see the response from the detector produced by a single photon. It's almost a 20 nanosecond pulse with some ringing, which is then filtered by our electronics, and then you count these pulses. Each pulse corresponds to a single photon. So we're doing single photon experiments here. And when you work with single photons, single electrons, single protons, you can actually exploit quantum mechanical effects. Quantum mechanics is how nature works. But generally, we are dealing with large systems, ensembles of systems. So that's why the quantum effects average out. But when you go to the grainy scale of things, look at photons one by one, you're actually exploiting and harnessing quantum mechanical effects. Now, you've learned, everyone learns about wave-particle duality. You can actually learn that light is a particle. It is indestructible, and it cannot be split up. And for this, we do a correlation kind of experiment, which classically is called the Hanbury-Brown twist experiment, in which we just, now, in one of the beams, we place a polarization beam splitter. Now, this channel, the A channel, signals that if a photon is detected on A, it signals that a photon must be present in this arm, because the two photons, the photon pair is produced in unison. They are produced together. They are entangled in time. So we do experiments on this arm conditional upon a coincidentally detected photon in channel A. So we only look at those photons which occur at B or B prime whenever there is a coincident pulse at A. So this is how we look at single photons. Now, what we observe here is that if this photon detector B gives a pulse, B prime doesn't give a pulse. It's just like a coin toss. You toss a coin, you either get heads or tail. You can't see heads or tails at the same time. So this is exactly a quantum coin tossing experiment. You look at a photon, either this detector fires or this detector fires. And this is plotted in the form of a correlation figure of merit, a second order correlation function. And this function drops to 0 at 0 nanosecond, which means you never detect coincident photons on B and B prime, or the photon is never split up into two. It actually shows the particle nature of photons. You can also measure what the quantum state is. Every system is described by a quantum state. So by looking at one of the beams and inputting certain kinds of polarization rotation elements, you can actually do tomography and find out what the polarization state of single photons is. And we can successfully do that. So these are kinds of plots that we obtain. We have complete control over what polarization state we can produce, and we can then measure or do tomography of these quantum states. But the nice thing about quantum mechanics and the counterintuitive thing is that a single photon interferes with itself. Now, on the one hand, we've learned that a photon cannot be split, but the photons, even though they are particle, they also manifest wave-like properties. Just like water waves can interfere, photons, which are nominally particles, they can also act like waves. We say that they are quantum fields, and these quantum fields can interfere with one another. And so we build an interferometer. In one of the parts of the photon, we have an interferometer which comprises a beam displacing prism, a half-wave plate, followed by another beam displacing prism, and we change the orientation of one of the beam displacing prisms, and we obtain this very nice interference pattern, which are called interference fringes, which actually shows that light has dual nature. It is a particle and a wave at the same time. And how it shows up in particular experiments depends upon the kind of experiment that we design. So our students are really excited and enthused to see that how you design the experiment becomes a part of the experiment itself. It affects and impacts what measurements we make, and our observations depend upon the kind of experiment we choose. It's just like saying that the moon is different when we choose to look at it. So here are some more experimental data from our quantum interference experiment. Depending upon the polarization state of this polarizer, we can create fringes of different visibility, all done with low-cost equipment. Someone who knows a little bit of quantum mechanics and has a good teacher at his or her disposal can perform these experiments and also understand these experiments, and can really appreciate that quantum mechanics is not to be closed out in a opaque box. It is a living reality. Now, the really strange thing about quantum mechanics is non-locality. Non-locality means that if I'm in Lahore and I share a quantum particle which is entangled with my particle with Dr. Shahbaz Anwar, who's in Cambridge, if I perform an experiment on my particles while sitting in Lahore, I can tell what outcome will Shahbaz will observe. Even though both of my particles on their own act like totally random coins. So if I get a heads on my coin, I will be sure that if Shahbaz flips his coin at the same time and he calls me up or emails me after his experiment and we share notes, both of us will get the same outcome. So this is called non-locality and is one of the most counterintuitive things of quantum mechanics. So we can actually test non-locality with our experiments as well. Sorry, I'm not seeing the chat box because I'm focusing on the presentation right now. Now, in order to look at non-locality, we do different kinds of tests. So if you look at the bottom left, we have a quantity called S. And S comprises expectation values. E's represent expectation values. And each expectation value is a combination of probabilities. Probability HH, which means first photon horizontally polarized, second horizontally. TVV, first vertical, second vertical. THV, first horizontal, second vertical, and so on. And then we build up these expectation values and construct this variable S. And if this S is below a certain threshold, we say that non-locality does not exist. Quantum mechanics is local. And if it violates this non-equality, we say that quantum mechanics is non-local. And we can look at this by producing a special state which is called the Bell state, which is entangled. So this is an example of a Bell state. So remember the coin toss example? My coin gives H, the other entangled coin also gives H. If my coin gives V, the other coin also gives V. So this is a prescription for writing a quantum state. So we prepare this state, we perform this experiment, and we obtain a value of S, which is 2.331, which is above the threshold 2. The standard error is 0.004. So you can imagine that we have about 600 or 700 times significance of our result, which actually shows that quantum mechanics is non-local. And we can do different kinds of tests. There's a Hardy's test, there is a Friedman's test, and no matter what kind of test we perform and design in our laboratory, we always see a violation of local realism, which means quantum mechanics is truly non-local and you cannot explain it using classical physics. Now I come to the last part of my talk, is measuring quantum states. Now when you build a quantum computer, what is a quantum computer? A quantum computer is an information processor that takes as input quantum states, performs certain transformations on the quantum states, and gives you an output. And the output then has to be measured. But doing something useful takes time. And when time is the real enemy of quantum computers. And why is that? Because quantum states are really fragile. When quantum states interact with the environment, they change. It's just as the environment is making a measurement. So quantum states change, and you would like to preserve the coherence of quantum states for longer periods of time, which means you don't want the states to decohere. And then you would like to do a measurement. Now, performing a measurement of a quantum state is called tomography. Just like one does CT scans, computed tomography of the human body, which means looking at different slices of the human tissue, you can also look at the quantum state of particles, which in our case are photons. And we can design experiments to measure the quantum state of photons. The experimental scheme is exactly similar as before, with the insertion of extra elements, a half-wave plate, a quartz plate to control the birefringence, quarter wave and half-wave plates followed by two beam splitters. And then in a sequence of experiments, you change the orientations of these plates and look at the probabilities or the number of outcomes, normalized outcomes on these 4 detectors. And then you change the orientation again, measure again, do it a large number of times. And from all the data that you've made, you then use a maximum likelihood algorithm that we employ to reconstruct what the quantum state of the light is that is coming into this crystal. And the quantum state is represented in the form of a matrix, which is called a density matrix. And there are 16 elements in this density matrix, and the height of these elements represents the elements themselves. So we can do complete quantum state tomography. This is some predictions, some theoretical predictions, and these are what our measured density matrices look like for different kinds of input states. And there is a strong overlap or similarity between the proposed density matrices and the measured density matrices. We can look at 2-qubit states, etc. Now we can also do really interesting stuff with these single photons. If you know, you might know about the Faraday effect and the Kerr effect. When light passes through a magnetic medium, its polarization state changes. And if you look at transmission experiments, they are called the Faraday effect, and if light is reflected from, say, a magnetic thin film, this is called the Kerr effect. So we can look at Faraday and Kerr effects of single photons. Just shine a single photon on a piece of material and see how the polarization of that single photon is changed, and what is the underlying quantum process that changes the polarization. So this experiment is called quantum process tomography. So in our laboratory, we do an experiment which is similar to the ones that I've shown before, but in one of the channels, we introduce a crystal. In our case, we use a terbium gallium garnet crystal which has high magneto-optic activity. We place it inside an electromagnet so that we can change the magnetic field, and we place the crystal inside a cryostat so that we can lower the temperature and can do temperature dependent measurements. One of the photon beams passes through this magneto-optic contraption, and then we do tomography of this photon. Of course, we need the other beam as well because we would like to do single photon experiments. So this, we can do temperature dependent experiments on single photons, magneto-optic experiments, and magnetic field dependent experiments. So magnetic fields change the quantum state, and then we can start looking at different kinds of by the way, we can also do a phase sensitive version of this experiment with the help of a lock-in amplifier. And then we can map all our results onto what is called a block sphere, which maps out the trajectory of the single photon qubits or the single photon quantum states. So here is an axis of rotation. As the photon passes through the crystal, the polarization state or the quantum state evolves on the surface of this block sphere. And we can look at the evolution of the quantum states on the block sphere as we change the magnetic field. So I would like to stop here, and I'd like to thank you for your time. I've tried to keep the presentation extremely simple in the interest of time, and keeping in view the broad audience that we have here. I'll be happy to take any questions.
Thank you very much. It was really very nice and light and broad presentation. And of course, we have many questions here. First, I would like to take this question with someone actually text. So it is someone has some, you can say, the problem in understanding duality of light. So his question is that how something can be particle and also wave at the same time. How would you comment about that?
You see, quantum mechanics is something really strange, and one of the strangeness of quantum mechanics lies in the fact that objects can can have dual character, and it all depends upon how you look at them.
Sorry, sir, we are still looking at your screen. Maybe you can stop this if you want.
Okay.
Sharing the screen, if you wish, because there is chat going on, I guess. Just to make it private.
All right. So particles and waves is this duality is extremely important. So in this example, if you have, imagine electrons. Electrons, when they are deflected by magnetic fields, they fall on certain screens, and if the screen is phosphorescent, they can glow. So electrons form shadows. So electrons really act like particles, but in some instances they can also act as waves. They interfere, and this effect is important when you do electron microscopy as well. So it all depends upon how you look at these quantum systems. And in quantum mechanics, how you design the experiment and how you measure and how you look at the experiment is actually a part of the experiment itself. Generally, in our laboratories, we look at a voltmeter measuring voltage. The voltmeter is something distinct from the power supply whose voltage you are measuring. But in quantum mechanics, both of them act together. The measurement apparatus, the measuring style of measurement, and the process itself, they act tandem to form a giant system. So the measurement process is very much a part of the process. And that's why sometimes you observe wave nature, sometimes you observe particle nature, but you can also design experiments in which you show both of these aspects at the same time. So this is the hallmark of quantum mechanics.
So maybe that we can say when we see, then it is actually the wave. When we don't see, it is a particle. For example, like a photoelectric effect, that it's a particle behavior in interference, that it is the wave.
Yes.
So now we can take a question from Muhammad Ramazan. Yes, please. Muhammad, could you switch on your mic? Yes.
Sir, is this possible to predict the same phenomena that is occurring in our Earth, and the same phenomena is happening and outside the world, which is actually not present? You may call it just like the matter and antimatter. Can you predict from the process of entanglement this one?
So maybe this is a question about metaphysics, but I might not be qualified to answer. But you can make predictions. So this is not something which shows our weakness about our understanding of nature. It actually shows our power. We can actually predict when we design these experiments. We actually know what and can predict what we should see, whether we should see the particle nature, the wave nature, what the probabilities are. We can do mathematical predictions of what the probabilities are. So we have complete predictive power over what we expect to observe in our experiments. It's actually, quantum mechanics is a theory, and a theory is based upon certain postulates and certain rules and certain laws and certain conjectures and ideas. So it's a holistic bunch of ideas, and with the help of a theory you can predict what the outcome of an experiment is, and you can predict it with almost 100% reliability. And quantum mechanics gives us this prediction power. So it's not something strange, or actually we know what's going to happen, and we can explain it with the help of quantum theory.
Actually, there are many questions. I would take only one final question because of the time. And Ali Hussain, could you please switch on your mic? Yes, please.
Thanks. Thanks for a nice talk. I have actually a couple of questions, maybe some are really short. So first of all, how does because I have a background in nonlinear optics, so I'm wondering how does the intensity noise of your laser might have an effect on your measurement? Like if you have one photon, you also talk about the short noise of the laser. So how does you tackle like the noise properties of your laser, or how does they affect your measurement? And also maybe another one related to this one is that you said that you have a very low efficiency in the BBO crystal. So does that put any limitation on your experiments in a certain way or not? Because you can get in a maybe 0.1% efficiency in these crystals and so on.
So, Ali, the second question first, the efficiency of these crystals is not even 0.1%, it's something of the order of 10 raised per minus 10 or 10 raised per minus 12%. It's a very inefficient process, which means that you need high power lasers to, high power means of the order of tens of milliwatts or hundreds of milliwatts, continuous wave lasers to actually extract a reasonable flux out of this crystal, so that you can be above the dark counts of your detectors. The detectors are really small dark counts, less than 100 counts per second. So that's our noise floor. And by the way, the low efficiency really helps us, because then we are able to do single photon experiments. But it can't be too low so that we go below the dead counts of the dark counts of the photodetectors. And your question about noise is important. That's why we try to use, number one, a spectrally pure laser, number two, a low noise laser. But then we remember that we are working with coincidences. Coincidences means two photons on the two detectors coming from the same source, which means one photon is down converted to give two beams, and that happens coincidentally. And you mark as a coincidence something that happens within 20 nanoseconds. That's our coincidence window. And with the amount of flux, the flux that you observe, you can actually count or estimate the accidental coincidences, which are not coming from the down conversion pairs. And that's extremely small. So we have to do all of these calculations to look at what the accidental count rates are, what the dark count rates are. And it turns out that with the fluxes that we achieve, we are way above the noise floor. So noise is an important consideration, yes, but it happens that we design our experiment so that we really go above noise floor.
Okay, I think now we should proceed to the next talk. Thank you very much, Dr. Sabieh Anwar. It was really very nice talk, and there are still many questions to answer, but unfortunately, because of time, we can't take them. So hope they will get later on. Thank you very much. Thank you. So our next speaker